Thank you. Good morning, everybody.
Right, well, hello, everybody. I'm Liz, the marketing manager at Sensor City. So welcome to the Sensor City Arrow Comes Home webinar series in partnership with Arrow Electronics. Today's session is the fifth and final webinar in this series, and the topic of charging and battery management will be a follow-on from the previous topics. We'll be joined by NXP today, who will be our guest speakers and electronics experts, of course, and they'll give a presentation with the opportunity to ask questions and answers. So if you want to use the chat function within this platform to post questions as the presentation is going along, that would be brilliant. If the microphones are muted by everybody apart from the speaker, that'll just help to reduce any background noise. But do use the chat function to keep active and pose any questions which will be addressed at the end of the presentation. We are recording the session today, and all the sessions will be hosted online, so you can listen again or focus in on a particular section at your own leisure. So the webinars that we have run over the past couple of months in this series focused on different areas of technology, and the energy storage and renewables markets are driven through some of these new technologies and serious growth areas. In particular, one of the most disruptive innovations in this field is the battery management system. And thanks to these devices, it is possible now to maximise the capacity of the battery stack whilst monitoring and balancing the battery cells. So to talk through this in a little bit more detail, I would like to hand over to Stephen Mitchell from NXP, who will lead today's main presentation. Thank you.
Good morning, everybody. Actually, I'm Steve Mitchell from Arrow, but I support all the NXP franchises. So I think I was in Sensor City last year doing Renesas, so I don't know if anybody was at that session. So we did a whole day doing a seminar on another MCU. So now I'm doing NXP, and I've been asked to do a battery management systems update. I had to think about this, and I thought I might as well give you kind of where the market is going. And so I looked at the most advanced stuff, and the most advanced battery management systems, in fact, is in automotive, because obviously there's a move to try and become greener. So these are sort of the most advanced management systems available, and I think this will be of interest to all of you because this is kind of where the market is moving, whether you're in automotive or non-automotive. So this is where the basis of my presentation will be. I hope you find this interesting. So what we've got at the moment, you can see four sort of classes of car. The basic system is on the 12 volt, 24 volt system. So we've got the 12 volt system, which is in normal cars, and 24 volt systems are in heavy duty HGV. And this is the sort of the standard car that we're all driving today. It has a 12 volt system, and it's basically charging up a 12 volt battery. But this is the old way of doing things. This is not the way forward. So moving towards the more advanced cell controllers, we've got something called a micro hybrid system, which is a 12 volt system with a 14 volt system, and this is using a more advanced audio front end from this NXP device. Moving a little bit more to the right, we've got something called mild hybrid, and this is a way to try and reduce the emissions by replacing the things that are connected to, say, the alternator belt, which is the camshaft, the alternator, stuff like that, with motors. And so the idea is that you use a 48 volt battery and a 48 volt generating system to rid the car of the cam belt. And this reduces the CO2 because it takes a few horsepower to actually drive that system. This is termed mild hybrid. Again, same device from NXP. Moving more to the right, we get into the more sexier part of the products, which is the hybrid electric vehicles. These are the devices that don't plug in, but they've got a hybrid system. So I think that's the new Toyota hybrid. You get the plug-in hybrid systems, which is the hybrid systems that use a plug-in, you plug in and charge it up. And you get the full EV systems, which are purely electric vehicle, things like the Nissan Leaf, the Tesla devices. And these are the systems that are kind of the future. So things are moving away from internal combustion more towards electric vehicles. And these require high voltage systems, so greater than 60 volts. In this case, much greater than 60 volts. So what we try to do, what NXP will try to do is create a battery system that kind of encompasses the electrification of vehicles. And the idea is to make it scalable, obviously, hard software compatible battery management solutions, supporting things like up to 212 systems per daisy chain. We'll go a bit more into that later on. But these are all driven by sort of complex software, of which NXP have lots of reference design, so you don't really have to do it yourself, because a lot of these things are safety critical. So there's a lot to it. And if you look a little bit into the middle, you'll see that the idea is to try and give you BOM cost savings. There's obviously complex cons between processor and battery management. We've got to guarantee isolation, because when you start looking at the voltages, they're really, really quite high. Accuracy is important, which I'll go on a little bit further on. Scalability, because we want one device to do multiple different applications. And safety, because a lot of these things are safety critical. If you take a battery today between 400 and 800 volts, in a car crash, you've got to be damn sure that 800 volts doesn't somehow find its way onto the skin of the aircraft, skin of the car. A worst case scenario would be in a multiple pile-up. All the car skins are connected together, and the poor sucker that grabs hold of the door may end up with a 400 or 800 volt belt. That's killable voltages. And what you'll find today is that the emergency crews in general wear gloves, because they don't know which car is electrified and which one is internal combustion, so you can't determine. And so this becomes quite critical, and safety becomes quite critical. It's kind of a worrying trend, but that's the way things are working at the moment. And so if you look at on the right-hand side, you'll see that the battery in electric vehicles worldwide is going up. This is quite an old survey. It's actually going higher than that, because petrol and is becoming, not green, and people want to go electric vehicles. So this is kind of a nice overview of where the market is and the different technologies that cars are using. So again, going into this tells you the kind of savings that we're looking for with electric vehicles. So starting with sort of a micro hybrid, conventional ICE, which is an internal combustion engine, with a 14 volt battery additional, you get a 4 to 6% CO2 saving, which is not terribly good. When we start going on to sort of the mild hybrid, so we're talking about, so you can look at the kilowatts that they actually require to drive traditionally the cam belt. It's up to 20 kilowatts. It's not insubstantial. It's pretty damn high. So when you start taking that out and replacing it with the 48 volt motors, you can give yourself a 50 to 20% CO2 saving. So this is worth having. And mild hybrids is in cars today. This is actually available today. Looking again towards full hybrid, this is the cars that are not plug-in but have a battery, and typically you're going to get, say, I don't know, 30 miles. 30 miles is a new BMW. It used to be 15, but that's now being regulated by the government, and it's now about how many miles you get out of the battery that determines your tax amount you're going to pay. So with a full hybrid, you're looking at 25 to 30%, 5% reduction in CO2, and that's very good. Plug-in hybrid, everybody rates plug-in hybrid, but there's a bit of a con with a plug-in hybrid, in that the batteries are so small that they don't give you a lot of miles out of it. And I've seen plug-in hybrids with as little as 15 miles out of the battery before it goes straight on to the engine. which is all very well, but you've got to remember you're carrying the weight of the battery with the engine, and unfortunately you end up with using more CO2 with these sort of plug-in hybrids. So this is kind of I'm not sure where the future of that one lies. And then on the full right, you've got the full electrics, which require, you can get 150 miles, 250 miles out of a Tesla, and these are this is where the market is moving towards. And if you look at the batteries, 400 to 800 volt batteries, so these are pretty dangerous beasts. And the idea is the government's got to use tax incentives, obviously reducing regulation on CO2, and trying to change people's mindset. There's also some, so look at you've got engine assist, regenerative braking. These are areas where you can actually gain energy back from the moving of the car. Start stop, which my car uses at the moment. I get to the lights, handbrake goes on, engine stops. I then just push my foot on the accelerator, it carries on going. So these are areas where you can actually save fuel. Okay, so where do these battery management systems work? It's not just automotive. So obviously, you've got cars, trucks, postal delivery trucks. In London at the moment are full electric. E-scooters and e-bikes looks like a kind of a future trend for maybe short commuting. But you've got things like balancing the grid. So at the moment, the government's trying to get everybody to use smart meters. And these smart meters are smarter than you think, in that once you plug your car in, the government will rebalance the grid by taking energy from your car and then balancing the grid and then paying you back when they can. So the idea is to have every house with a smart grid and maybe a car charger, and then they can then balance the grid by taking energy from your car, replacing it as and when. So this is what they call balancing the grid. Also, what you're finding now is that there's a lot of companies now using large storage batteries in the house, and then you can use your solar cell, your wind power to charge up. Not if you can't use it today, you can charge up a battery. One of the biggest issues we've got is we've got a lot of wind turbines that sit idly by because we don't need the energy at the point that they're actually turning, but we can't store it. So the biggest issue we've got today in the moment is not the generation of electricity, it's the storage of electricity. So by having these home batteries, then you can store your energy. So we've got a company in the UK that take the Nissan Leaf batteries after, I think it's 5 years old. They're still at about 95% capacity, and they repackage them and put it into a big stack of batteries that you can put in your house, and your charging system can then charge that, so you can get energy when you need that. Obviously, interruptible power supplies is obviously a requirement for batteries, because in some certain circumstances you can't afford, like a server, to go down with a power supply interrupt. Hospitals can't possibly do without power if you're in an operating theatre. There's one I know that which is done in Swanley in Southampton, and all the radar information for the entire country goes into this one place where they do all the air traffic control for the UK, which sounds a bit iffy. They definitely need a UPS, and in this case, it's the requirement is from standing start to 4.5 megawatts in 5 seconds, which is amazingly high speed. So these are the sort of things you need the UPSs for, and again, batteries can help you with these sort of things to start things up. Obviously, you've got robotics, automotive guided equipment, forklift. These are all becoming more electrified. So these are areas where battery charging is going to be quite useful. Sorry about I've not done all these fancy PowerPoint stuff. I've inherited this, so apologies for this. So there's different types of battery technologies, and they're all slightly different. So you've got the traditional lead acid, you've got the kind of NiCads, nickel metal hydride, and the one that gives you the best general performance is lithium ion. And within that, there are different types of lithium ion. So You've got things called LPF, which is lithium iron phosphate, which was produced, created 1997, 96. It's a very safe battery. The Chinese government tend to like it, and it gives you per cell about 2.5 to 3.7 volts. You've got another lithium technology called lithium titanate, developed in 2008, which is long life, fast charge, and very safe, but high cost. So between 1.5 and 2.7 volts per cell. And you've got something called lithium nickel manganese cobalt oxide, which was again in 2008, high capacity, power increasing market, but less safe, between 2.5 and 4.3 volts. So lithium ion is kind of a banner term for a lot of different chemistries, and the chemistry is relative to what you want out of the battery, the safety, the temperature range, depending on what you want to do. And this is all part of the calculation as an engineer that you make when you design a piece of equipment. You need to know where it's going to be used, how it's going to be used. Yes. Okay. So the type of battery technology, the protection is very, very important, because lithium ion has very high power to weight ratio. It's kind of like if you use it the wrong way, it's a bit like a bomb. It can explode. You've got to be very careful. And with the battery charging technology, it's got to consider all of these points and make sure it's safe before it does these things. So battery over voltage, lithium ion do not like to be over voltaged. They will trigger a reaction. The battery will overheat. You'll get smoke. So this is pretty damn dangerous. So this is definitely something you want to check for. Thermal runaway. This is something that happens when a battery starts to charge up to fully charged. It's still chucking charge into it, and it starts to get temperature. It starts to heat up, and unfortunately, because of the positive temperature coefficient, the hotter it gets, the lower impedance, then more charge, more heat, etc., etc. This is called thermal runaway. Again, you definitely don't want that, because you're in a dangerous area. You've got undervoltage problems where if you undervolt a battery, now this is done on a cell by cell basis, so it's not the entire battery. It's got to be looked at a cell. These are all cell by cell protections that you've got to do from the battery management system. So every cell's got to be checked for an under battery voltage. So you get electrical breakdown over a few cycles. So once a battery cell gets below 2 volts, then you're in this dangerous area called battery under voltage. Battery overcurrent again can be a problem. You cannot charge it faster than it really is designed to do, because it's a safety issue. So you don't just plug in a lithium ion to any old charger. It's got to be one that's capable of charging a lithium battery. So these are things you've got to be aware of. Even under temperature is an issue. Not only is it dangerous and damages the battery, you get a much lower capacity battery. So if you get in your car when it's 0 degrees, you'll get your miles to its M2 will be a lot less than if it's at 25 degrees. So this affects the chemistry of the battery. So you've got to make sure that it's within the temperature range. And this is again, you choose the chemistry of the battery relative to the area you're going to operate the actual battery in. So I mean, these batteries are on battery cells used in, say, like cars or industrial machinery. So battery cells, a basic unit of a battery is lithium-ion battery has an output of 2.5 to say 4.3 volts, and depending on the chemical type, you have to sum up the battery. So a 14-volt battery will typically be, say, 4 to 6 cells. An 800-volt full EV battery system needs about 190 to 250 cells to give you the voltage. And then you parallel that up to give you the current. So you can end up with 1,000 cells in a car, easy. So a lot of power, a lot to go wrong. So the main functions of a battery management system like a 33771 is to monitor the cells voltage, current, and temperature, and then report that back to the MCU. So the management system is looking at all these areas, and then you then interrogate the chip, get the results, and then you then determine what you're going to do about it. So there's two parts to this. There's the battery management chip that makes the measurements, and then the MCU acts on it depending on what the results are. So this is the MCU which determines the battery state of health. SOC is a term used in battery technology, and then it determines its state of health, SOH, as well. So the idea is that you need to use things like cell balancing to make sure all cells are at the same rate. One's not more charged than the other. One's not completely discharged, in which case you're in this dangerous area about undercharging, and you take appropriate measures. So that's the idea of it, and that's what these chips are going to do. It's not a sort of thing you do yourself without an awful lot of knowledge and a lot of analog experience. The idea is that you put these all in one chip, and it does it for you, and you basically don't do any of the complicated things yourself, because it will. There's a lot of things can go wrong. Let's put it that way. And typically, these sort of chips have an SPI. I'm hoping you guys have got sufficient electronic understanding to keep up with this, and things called Coulomb counting for counting the charge going into the battery. And the internal resistance calculation is this thing where you're looking at whether it's going to thermal runaway. These are the conditions you're trying to make sure that the battery stays within limits. So going back to how it's connected, you can see that the one on the right is a stop-start, which is kind of where my car is at the moment. It's a 12-volt system, but it's got stop-start technology. And if you're in London, that makes a lot of difference. So you've got something called an SBC, which is the power controller for the MCU. I'll come back to that because there's an important point to that. There's an MCU, and then there's a battery charging system. On the right, as we digitize it a bit more, you've got multiple voltage sensing, current sensing, temperature sensing. That's the V, the I, and the T. And this is the stop-start 14-volt lithium battery. Going a bit further right, you can see that you've got the mild hybrid system, which is trying to get rid of the cam belt. And then on the right-hand system, full electric. This is the top of the range, seriously expensive, all-electric car. And you start summing up these battery modules, and you've got to have them all communicating back to a main MCU, and the main MCU has to be able to interrogate any one of them via these COM links. So you've got 800 volts at one end and 0 volts at the other. So you can see there's a lot of isolation involved. So there's a lot of engineering in this. I hope I'm not scaring everybody. So if we look at the type of things that you get in one of these chips, you can see it's quite complex. So by and large, it uses something called a fairly configurable ADC with hardware filters to reduce the software complexity. Now, if you look at the product, it says 3 times 16-bit ADC. You need an ADC at 16 bits because typically a lithium-ion battery is pretty flat, and then it suddenly drops off at the edge. So if you're trying to find the point where it's starting to drop and it's only millivolts and you've got volts, you need a pretty high-end ADC. So this is why you need these high-end ADCs. It's trying to find out where exactly it is on this fairly flat curve to work out whether it needs where it is in its capacity. And it's obviously doing current and voltage and temperature. So it's got things like voltage sensitive inputs, internal dividers, VSense, up to about 52 volts per chip. Now that's not the battery, that's just the chip. So that's the module. The battery module can have a maximum of 52 volts. So you series up the batteries, and 52 volts is the kind of the max that this chip will be able to take. in that one battery module. And you've got sense errors of sort of like 0.25%, 15%, you know, with 4-volt cell measurements of 10 millivolts. So it's pretty accurate, and resolutions of say 0.25 millivolt per LSB. So you need pretty accurate analog capability within this mixed signal AC product. So the idea is that you have to synchronize your currents and voltages, so you're doing both at the same time. And this is kind of does this in about 10 milliseconds, so it's relatively accurate. So the idea is that you've got your MCU, and that's then interrogating the analog battery management system. It's called the BMS, and this is then making these sort of decisions of what you actually end up doing with this particular cell. So there's sort of two parts that are used, and it depends on how many cells you want in the system. They're mostly the same part. It just depends on what you actually want. So, and this is your stack voltage measurement. So there's something called a Coulomb counter. So, and this has got to be accurate. So you can see you need a high granularity. So it's from microamps to, I think this maximum that this thing can actually measure is 1500 amps. So you need pretty accurate current monitoring to actually be able to give you that sort of granularity. And you need to synchronize your cell voltage and current measurements so that you know at any one time what's actually going into the cell or the battery module. And you're monitoring your temperature and your voltage. Cell balancing is once you start charging a battery module that has multiple cells, you've got to try and look at all the voltages across all the cells and make sure they're all about the same voltage. Otherwise, you get an unbalanced battery module. So that's what's called cell balancing. This is actually quite important because it'll cause a failure. You'll get it won't be as long lasting. So this is an important aspect. Now, something that is becoming quite important, and everybody will get involved with this at some point, is because these things are dangerous, they're high voltage, they're high current, they're kind of like a bomb because they've got a lot of power per unit volume. These things are now classed as need to be designed to something called ISO 26262. This is a safety specification, and the automotive variant of that is called ASIL, Automotive SIL, and there's A, B, C, and D, and D is the highest. In industrial applications, it will just be called SIL 1, 2, 3, and 4. Same thing, but there's an automotive variant and there's a industrial variant, but they're all based on this thing called ISO 26262, which is a safety specification. It's an ISO specification. So you will get involved in this, and this is where things get a bit tricky because you need fairly specialized electronics, which we will go on to in a minute. The comms between the battery modules, so from one battery management system 3371 to the next 3371 is on either an SPI or something called isolated transformer interface, which we'll come on to. Okay, so this is like a typical application. So customers today looking to replace some sort of a lead acid 12-volt battery with lightweight lithium ion for the start-stop systems. The 772 is a perfect fit for this use. It's got an integrated measurement, integrated cell balancing, and an SPI. This is a very simple application, kind of very small battery application. And you can use an SPI into the SPI interface within it to make this thing as a unit to the main microcontroller. So this is where things get slightly more complicated. So if you're looking for an ASIL or a SIL application, because this is because it's safety critical, you can't afford it to go wrong, you have to use something called an MCU that's capable of SIL or 26262 compliance. and this is typically used by something called a microcontroller 574X. This is a particular processor. It's called lockstep. It has two separate cores. They both run in the same application, and both cores have got to agree before the actual it's actually allowed to do anything. So these two things are running, and I think they're one clock behind one another, but the results got to be the same. And the die in one is 90 degrees from the other die. So if you're flying up high and you get hit by an alpha particle, it doesn't black both processors at the same time. So if you want a 26262 application, you would use something which has got something called dual core or lockstep. Lockstep's the important bit. If it's a non-safety critical application, then you can use a standard microcontroller like an S32K, which is an automotive, but there are variations that are industrial. These are standard M0, M4, or M7 Cortex, ARM Cortexes. I'm hoping everybody knows what an ARM Cortex is because it's kind of an industry standard. So for this 12 battery architecture, the cells are all connected to this thing called an AFE, which is the analog front end, and this is of the 3370. So you see all these C6Ps, 5s, 4s. These are the cells, and they're all connected to the battery management system, and it's doing checks on the battery pack, on a battery module by battery module case. So in this case, there's 6 battery modules in this pack. So the 3 temperature sensors, there's current sense with a shunt to offset the compensation for higher current accuracy. There are redundant current measurements, requirement for ASLC applications. There's a VPAC, voltage redundancy for safety. There's a V-Link voltage management for GPO for diagnostic purposes. The communication in this case is because it's not daisy chain, can be via SPI. And the MCU should be lockstep for safety, but doesn't have to be if it's not not safety. There's something called crash signal detection. Now, this is an automotive one, but you should be aware of it. Because I said if this battery terminal gets towards the skin of the car, you've got potentially killable area. So there's actually, if in a crash, this determines if it's in a crash and then completely disconnects itself from the system and therefore from the skin of the car. So the idea is that in a crash, the battery becomes effectively disconnected from the whole car. That's a safety application. So in this case, the BMS is powered by the T30, which is on the where's that? It's on the right-hand side, the 12-volt main battery. From the 12-volt battery, and the application can be switched through T30. So car communication, generally car communication is done through CAN. It doesn't use LIN, and CAN is a very interesting industrial interface for high noise, high reliability, up to about. Standard one was 1 meg, but there's something called CAN-FD gives you up to 10 megabits per second. So it's pretty high speed, and the relay control can be bistable or monostable. Usually you're looking at a 10 ampere hour in the case of lead acid, although it's not enough to crank the engine. So this is a sort of typical application. The SBC, I'll come back to that, but the idea is that the power. The DC to DC device powering the MCU, if it's in an ASIL one, has to be specifically designed to be in the safety application. So in this case, the SBC power device in the middle of the screen to the right of the microcontroller also is able to interrogate the micro, and so the SBC can actually send like a randomized seed to the MCU. The MCU then has to calculate and respond back. The SBC will then determine whether the microcontroller is running properly, because it's a bit like an encryption goes one way and the encryption comes the other way, and if you get it wrong, the SB says the micro is not working properly, shut it down. So this is part of this thing called an 26262 combination, where you make sure that you've got separated microcontrollers with dual lockstep, and even the power devices are doing communication with the micro to make sure it's able to make the calculation. This is quite complex. This is quite normal. So in a car, you'll typically get, if it's an SLD system, you'll end up with 400 meg processor, 32-bit, and sort of 90% of that entire processor bandwidth will be checking that it's capable of making that 10% actual work for the car. So most of the time, the micro is just checking that it can make its own. It is allowed to make the decision when it comes to it, which is important in a battery management system. It's important with things like airbags, active suspension, active steering. All of these things come drive-by-wire. You can't afford these things to go wrong because you're in serious trouble. I hope I'm not scaring you guys. This is that's what I'm saying. The car guys are way ahead of everybody else because this has now been deployed today. So what you'll see in your future battery applications, the battery charging, battery management systems, is this is what's happening today there, and this is what's going to happen tomorrow in everything else, because these guys are kind of at the forefront of demanding more and more complexity, and which is good for you guys, because a lot of these are in reference designs, which you'll see later on, and you'll find it you're ahead of the curve effectively. This is not standard battery management stuff. This is advanced battery management, and this is something to know about. So this is a standard lithium-ion, 14-volt lithium-ion starter battery system to power the BMS. It needs to be coming from the battery itself. It's difficult to achieve low sleep current with this, usually sort of less than 100 microamps, while keeping the monitoring of the cell. So even when the car's off, it's still got to be doing monitoring. So this is something you need to keep into consideration. You can use a LIN communication. Just to go on, LIN is a kind of differential UART type thing. It's a much lower spec than CAN, but it's a much cheaper implementation. Because in a micro you can use a UART. Again, I'm hoping you guys know what that is, to do through something called a LIN transceiver to create a bidirect differential communication at a UART type bit rate. And you can see that the contactors are still needed to protect the battery from overcharge and may lead to thermal events. So that there's a contactor there, and based on the communication between the 3372 and the micro then decides whether to throw the relay or allow it to charge. So it's a fairly simple system, but you can see what it's trying to do. The relay is a monostable, cannot be used here due to the high consumption of 2 to 5 watts per contactor closed. And to keep the relay closed, even in the case of power loss, only a bistable relay can be used in this case. Application limited due to lithium-ion performance at cold temperatures, especially for cranking operations, although some cell manufacturers are kind of claiming that they have enough capability to do cold cranking with the improved lithium-ion technology. Cranking can take 100 amps, so it's a big deal. So this is the mild hybrid system. It's very similar to the other ones. You can see the relay, but you've got a 12-volt system. You've got a 48-volt system, and we've kind of gone through what the differences are. But again, you've got this thing called now. You've got this transformer device in the middle, because this is allowing us to use more and more batteries, and you have to start linking them up, and then the microcontroller will have specific voltage maximums, and you can't expose a large voltage to these ASICs because they blow up. So you need to now start using isolation technologies, and transformers tend to be the type of products used because you get relatively high speed and you've got proper isolation. What else is there on this? Let's see. Yeah. So this is where it gets much more complicated. It doesn't look complicated, but believe me, this is more complicated. This is when you start using these cell modules, and there's multiple cells in this module, and you now have to have your battery management controller is now looking at communicating with all of these products. So you can see this on the right hand side, that dotted line, CAN or TPL. You're starting to use TPL more because you've got this transformer isolation. So you've got BMS system has a sort of like a TPL in and a TPL out, and you can then daisy chain all the battery modules, and then the battery controller can then interrogate the individual cells and get information back to find out the state of the each cell within the module and the state of all the modules. So you can see these things are actually working pretty damn hard. And at the end of the battery management controller, there's an MCU making that sort of decision. And if you look in the top right, you can see these things are pretty complicated. So there's a lot to go wrong. There's a lot to monitor, and they're damned expensive as well. So you don't want to push something out that which costs thousands of pounds, frankly. So there's a thing at the bottom. You can either use the bottom one is on the 3371 can do the current shunt, but in this case you can actually do it with using the battery management controller, because the battery management controller can do that sort of thing. So in the chain, the advanced version, which omits the current sense measurement, alternatively, the current sense function can be integrated in the battery management switch box, which is as it's drawn at the bottom. So you can do either. So this is a bit more diagram on what it looks like. So the battery module is connected to the battery management system. There's an Ethernet transformer. This is the TPL that goes back to the physical interface. So the TPL then gets converted into SPI technology, and that's what the 3364 is doing. So TPL on the left-hand side, SPI on the outside. So you've got high voltage on the left-hand side and more normal voltage, 3v3 type voltages on the right-hand side of the physical interface. And this then can go back to the microcontroller. This is a standard microcontroller, so this is not safety critical. And then you've got the safety basis chip, which gives you all of this, not only LDOs, watchdog, CAN-FD, and wake-up capabilities. So these system basis chips are not just power; they've got a lot of extra functionality, and they're quite useful and used quite heavily in this sort of application. So on higher voltage products, you've got a sub-pack concept which is implemented in the 771 with this TPL approach. So the TPL is this transformer isolation-based comms. The CT is the output cell test, which you test each cell continuously. And cell balancing is when you try to balance the voltage amongst all of the cells in the module so that they're all at the same voltage. Which is quite important. Is this one much useful? No, I've explained that one already. Sorry. Now I'm not going to go through this, but this is kind of this is the whole of the chip. So this is for a high-end 14-cell battery module. And on the left-hand side, there's a whole raft of features, which is far more complicated than we need. But at the bottom, you'll see it's ACQ100 automotive qualified. That's full automotive. So this is good up to 105 degrees centigrade. You can get higher, but then you have to use TPL for comms, which I'll show you this. So if you look in the bottom here, the temperature range, -40 to 125 SPI and -40 to 105 TPL communication based on the temperature range. So under the bonnet in a car, you have to have electronics designed for minimum 125. Typically, they're now pushing for 150, believe it or not. So this is where it gets a bit more software-y, but basically this is the kind of this is inside the battery management system and what it's looking for. So in idle mode, it's kind of powered down, no messages are recognized, and it's looking for a valid wake up. It lets then transition from idle into initialization mode. So in normal mode, the 771 is performing all the communication, all the ADC conversions, and allowing the micro to then get the information back. You can put it into sleep mode to try and reduce the amount of power dissipation, because obviously you leave a car for a long time, you can't have it drawing lots of current. but you still want to have the over voltage, the under voltage, over temperature, under temperature, active and reporting back if it needs to. So even in sleep mode, it still has to be to a certain amount, doing some calculation, doing some checking to make sure the battery's fine. And then there's a diagnostic mode that the MCU can put it into to do some diagnostic modes. This is software. There's a lot of software involved in this, and what you will find if you use an NXP processor with this part, there's something called an SDK, software development kit, that you can drag in a project and it will all work. And it's all source code, but it's all guaranteed to work, which I think there's some stuff at the end of this presentation. Let's go to the next bit. This is the actual transformer in the transformer physical layer. So this is taking in transformer information on the left-hand side, and out comes a differential SPI on the right-hand side. So this is just a way of doing transformer to SPI. So it's a conversion from one comms to another type of comms. And physically, you can see that you've got TPL. If you've got a whole bank of these battery modules, you need 133771 for each, and then you daisy chain them up so you can go all the way down to the bottom, and you can see the battery pack controller then taking the TPL information in, out comes SPI, and the MCU is then looking for each and individual cell amongst each of the individual battery modules. So this is how it typically is connected up. It's quite complicated, but now this is the type of transformer that we would recommend. This is the one that NXP have on their reference designs. They've qualified it. They're happy. It's full automotive qualified with industrial versions of it. But this is the sort of stuff that you would use for your transformer interfacing. So to give you talking about the centralized lid, up to 15 nodes on one EVB. So that's fine, because on a 3371 it's up to 14 cells. So this is actually has more capability than the device. So you've got enough modes, and the 15 nodes is to do with the 10 milliseconds capability when you measure a thing to get it back to the MCU to make a decision. So the TPL isn't super fast, but it's robust. So the 15 nodes gives you that capability. And on the EVB to the top right, these are dev boards that we produce, NXP produce, sorry, and this is sort of what it's capable of doing. So you've got these dev boards that you can purchase, or if you ask somebody at Arrow very nicely, you might get one for free. So this is to do with the nodes. So you can see by using the TPL and these pulse transformers, you've got the node quantity, the number of nodes, and the length of cable between the nodes. So with one node, you've got 100 meters. That's what it's capable of driving. If you've got 5 nodes, you've only got 10 meters between the nodes. Now, personally, this is much more than you need, because battery packs are really quite tightly packed. So this is very conservative stuff. But you could get baud rates of 2 megabits, so it's really quite impressive. Or CAN, if you want to use CAN. But then you've got to worry about isolation. You need to use isolated CAN transceivers. So it's a mix and match of what you want to use. This is just basically different types of parts. So obviously the 3371 comes with lots of different features, and you basically choose what features you want. And there's a price difference between these sort of products. So this is not terribly interesting, but that's the point of this product or this page. And again, if you look at the part numbers, you can make up the part number based on what you're trying to do with your lithium-ion battery management system, and you pick the appropriate part. So this is nice and easy to actually create the part number you need based on the feature set that you're actually trying to get to. Differentiating points. So why this is the industry leading device at this moment in time. So 2 megabits per second comms, 100% differential programmable address bus wake up. It has 3,750 volt isolation, with an IECQ 200, which is a passive automotive spec external transformer. This is the pulse transformer. It's got termination resistors for common mode immunity. It's got current gain error measurements, gain error of offsets. So it's got a lot of capability that allows you to do this sort of applications. A lot of this stuff you don't get involved with too much. What we would give you is a reference design for you to play with, and then you take the reference design and then apply it to your own application. Reference design, super cool. So these are sort of the reference designs we get. So this is a nice simple one to get you going. You've got, although it's got quite a complex lock step part on there, in truth, I would probably use something like an S32 device, or an LPC, or an NXP K microcontroller. The MPC 5744 is lockstep, but that's a high-end product. You've got 48 volts in. This is getting towards your mild hybrid products. So there's a nice dead board for that. It gives you the part numbers. Again, 5744 is quite a high-end part. In practice, you might prototype with it, but in production, I would use something else if it's not going to be an ASIL ISO 26262 product. We have proper reference devices, reference boards, and reference designs. Again, you get these. You've got the schematics, you've got the Gerbers, you get the boards. It should be relatively easy to plug down what you want. And even the microcontroller comes with source code. It's better to use maybe the NXP one, because we will guarantee the product will work, because these are all developed in Austin or in Germany. So these people sit together, they guarantee it will work. But the source code is the source code. You can use another processor. It's just, you won't therefore then get the support, because you're using a different processor, and NXP are not as familiar with another processor as they are with an NXP one. Compatible drivers. So this is what's called the SDK, Software Development Kit. So with the when you use the development environment from NXP with their micros, a lot of this software is written. So these are all the kind of the commands that you send the MCU to control or read information back from the battery management system. So this all comes with the SDK. Again, it's in source. You don't have to use NXP. It's just easier if you do. Enablement tools. So these are the dev boards. Let's get up to speed. There is an evaluation setup, so you do have an application on your PC that you can connect up a dev board. You can play with the features. You can play with the control, the measurement, and you get a feel for it in a safe. Obviously, it's got to be safe. GUI to allow you to see the comms between the processors, and you can quickly get an application. And what you will find is that the dev boards. So the dev board at the bottom is the NXP processor, which is in this case a KL25, and it fits onto a BMS board on top, and it just plugs together. The GUI software runs, it automatically detects, and it works. This goes into a bit more depth of what is capable of it, and the kind of the flags and the register settings of the individual chip. Support will probably come via me, but you can also, if you come to me, I'll be in the queue quicker than you. If I don't know it myself, I can then raise a ticket. That's going back to the design people at NXP if I don't know the answers. And I think that's the conclusion. Is that all right, guys? 10:55. I think I was right on the button.
Brilliant, thank you very much. We have had a couple of questions come in on the chat. So the first one was, are battery management systems linked to cloud computing so you can see their data and charging status online in real time?
So I need to turn up my volume on the speaker. Hang on a second. It's a bit low. Can you repeat the question?
Yep. Bear with me 1 second. So are battery management systems linked to cloud computing so you can see their data and charging status online in real time?
You certainly can do that. I don't know if anybody's doing that, but you certainly can do that. Cloud computing is kind of the norm. I suspect in the future it will become, because one of the things that you will probably end up doing is a lot of equipment will be sold, and instead of putting a black box in the end equipment, you probably, if you connect it to the cloud, you can then save money on the black box and do real-time monitoring in the cloud, and that gives you an indication whether the end user has abused their product, in which case the liability is not on you, or whether there's in fact a problem with the product you produce. So it does seem like a pretty reasonable thing to do in the future, but you've got to guarantee cloud connectivity, and if not, you need some sort of way of data logging it and then and then connecting when you can. But that would seem quite a reasonable thing to do.
Great, thank you. This was a question that I actually had myself. So like the batteries that I use on a daily basis are in my mobile phone and laptop. Yep. So do these use hybrid batteries, and how can their life be extended or maximised?
No, that's all done by the mobile phone. The phone guys spend lots of money on maximising battery usage. There was a thing with Apple where what they were underclocking the clocks as the batteries got older, because they're monitoring it and seeing that the battery voltages are not as good, so they were actually underperforming the processor. So the mobile guys are doing that, and they've been doing it for quite some time. They just don't talk about it.
Okay, and then we've had a final question. It says, please could you go into a bit more detail regarding the SoC and SOH monitoring capabilities of the MC3377x?
Ooh, where's that? 1 second. Page number. Well, I mean, if you look at it, no, I don't really need a page number. It's right at the end, really, thinking about it. But if you look at the command codes from, where's it gone? Hang on. No, not that one. Hang on. Right, so if you look at that page there, you've got commands you can send between the MCU and the BMS device. Now, based on the information you get back in terms of currents, voltages, temperatures, you then determine what you want to do with it, depending on the battery chemistry and what sort of performance and control measures you want. If you use the SDK, a lot of that's been done for you. So if you're looking for SoC and SOH, how it's defined, I would suggest maybe you talk to your local FE-RO and get a couple of dev boards, and then go through the dev board and then see how it actually, what it determines the SoC and SOH. So this is based on the chemistry of the battery and the measurements you do, and that's voltage, current, and temperature. And this is, so actually, even if you don't do that, you can just download, if you downloaded MCU Expresso with an S32 and then downloaded the SDK, and then you can go through the code. It's just easier to do it if you've got the boards, because you can set breakpoints. So it depends on the chemistry and how you use it and the data you get back. It's a difficult question because the SoC and the SOH is the kind of the key thing to all of this, because this determines how long the battery is going to last. Is the battery being used in a safe or unsafe state? So this is the art, so this is a deep question, in fact. I might be able to, if the guy's got my email address, we can go maybe do this in a bit more detail, or I can give him some more information after the event.
Great, thank you very much. So yeah, thank you very much to Stephen for his very insightful and detailed presentation. I hope everyone's learned a lot more about advanced management systems in the automotive industry, but also its applications across other sectors. It certainly did help to build on our previous webinar, which was focused on the electrification of transportation. So it's great conclusion to our series today. So thank you very much to everyone who's joined us today and also across the previous webinars. All of the sessions have been recorded, so you can catch up with them at your leisure. They're all hosted on YouTube, and we'll share details on our website so you can review them at your leisure and focus in on any specific topics that you found of particular interest. So if you do want to visit sensorcity.co.uk, you can find all of the webinars there, and equally any details on future events that may be upcoming, whether that's further online webinars with different presenters and organisations as partners, or hopefully in not the too distant future, we will be able to get back inside of our Innovation Hub to host events in person. So if you do have any feedback or any ideas for future sessions that you'd like us to run, please do get in touch. I will circulate a link to the recorded session and the slides from today following this presentation, but do keep in touch and please do get involved with Sensor City going forward. So I'd like to say a big thank you again to all of our attendees, speakers and Arrow Electronics, particularly Harry, Dane and Ryan for all their support in pulling these together. So hopefully we'll see you all again soon, but bye for now. Thank you.
Bye.